Hey everybody, so we are in section 10.3 and we are looking at something kind of new, pretty fun topic, at least I think so, and that is polar coordinates. So we're going to learn an entirely new coordinate system today and do a bunch of examples with it, try to get you guys familiarized with this concept. A bit of a longer one today, so let's go ahead and just dive right in. So typically what we've been using just throughout our entire mathematical careers up to this point have been Cartesian coordinates, and these are also called rectangular coordinates, but we call them Cartesian, particularly after René Descartes, who was a philosopher and mathematician who ended up creating this coordinate system. So we use the point x comma y to determine a point in the plane using horizontal and vertical components, right? So if I start right at the origin here, and then we say, okay, well, this point over here, we can define it by moving over, whatever, 2 units horizontally and 3 units vertically, and then we get the point 2, 3, like this. Oops. So something like that. You get the idea. Okay. But now, what we're going to be working with in polar coordinates is the idea of, instead of moving horizontally and vertically, we're using rotation and distance from the center of, say, a circle. So we draw a horizontal ray called the polar axis, beginning at an origin point called the pole, typically pointed in the direction of the positive x-axis. So here you can see there's our positive x-axis. Okay. And then to determine any point P in the plane using this system, we let R be the distance. So here's the point P. We let R be the distance from O to P. So O to P, so that's R. And let theta be the angle between the polar axis and the line segment OP. So this right here. So that is our theta angle in there. So the point P can be represented by the ordered pair r comma theta. Okay, so we have r comma theta. Okay, so common convention says that positive values of theta are measured moving counterclockwise. So just picture what we normally do with the unit circle, right? We have our axes, and we start over here, and then we draw our circle counterclockwise like that. Okay, so it's the same kind of thing. So standard convention. So this is our polar axis. Oops. So you have to pardon my extra bits of writing here. I just got a new stylus this morning and still getting the hang of it here. Okay, so again, we start on the positive polar axis and move counterclockwise. So we say the value of negative r comma theta is on the same line as r theta, but on opposite sides of that origin or that pole. So, right, if we had a point P out here, which again, this is the point r comma theta, okay, then the point negative r comma theta would be along the same line, but down this way. And that would be negative r comma theta over here. Okay. So let's look at a few examples here. So plot the points whose polar coordinates are given. So we have 1 comma 5 pi over 4. All right. So let's just draw that origin point, our polar axis. Okay, so that's O. Okay, and then the r value tells us how far away from the origin we are, and then the theta value tells us how far around we go. So 5 pi over 4. So you are going to need to brush up on your unit circle a little bit. You do need to know where all this stuff is. So 5 pi over 4, that's going to be pi plus another pi over 4. So that's going to be right about here. And so we have this line right here and that point right there. Okay, so this is going to give us, so here's our theta is 5 pi over 4. Okay, and then our R value is 1. So this point right here, that's the point 1 comma 5 pi over 4. There we go. Okay, let's look at the next one. So 2 comma 3 pi. So get my polar axis there. There's my starting point, O. And then, so we're going 3 pi. Alright, so starting here, we go around, there's 1 pi, 2 pi, gets us back to where we started, and then 3 pi. Puts us right over here. And the radius value is 2, so we're going to go out 2 units. So there's 1 unit, 2 units right there. So that's our point 2 comma 3 pi. Alright. And then part C. So we have our polar axis here. And we're going negative 2 pi over 3 for the angle. So we're going to head in the negative direction, 2 pi over 3, which is going to put us, it's just a little bit more than 90 degrees, right, or pi over 2. So that's going to be right about there. And just try to imagine that that's a straight line. There we go. So, and again, so this angle here is negative 2 pi over 3. And then this length is 1, 2 units. So that's the point 2 comma negative 2 pi over 3. Right down here. And then last one, negative 3 comma 3 pi over 4. So for this one, get my polar axis going here. So 3 pi over 4, that's going to be right about here. Okay, so this would be our polar axis. Okay. But because we're moving r is negative 3, then we actually don't want to be on this positive portion of the axis, right? Because this is theta is 3 pi over 4. 3 pi over 4. But we want to be on the negative portion because r is negative 3. So we're going to actually go down this way somewhere over here. And we're counting out 3 units. So say 1, 2, 3. So that's negative 3 comma 3 pi over 4. Alright, so that puts us down in the 4th quadrant over here. Alright, so again, sorry the drawings are a little bit a little bit wobbly. But again, this is just another way of plotting points, this time using angle of rotation and radius length, right? Distance from origin. Okay. So we can actually look at the relationship between polar coordinates and Cartesian coordinates using a right triangle. So if we set up our angle, so this is our angle theta. Oops. Doesn't want me to do that. Well, so let me put the coordinates on here first. So that's x. That's y. This is r. This is our point P, right? R comma theta. Oh, we don't need P for this one. Just want to look at the triangle. And there's theta. Okay. So trying to get a relationship between r and theta and x and y, we can use trig. So if we look at the cosine of theta, that's going to be right, adjacent over hypotenuse, so adjacent over hypotenuse. So that's going to be x over r. And sine of theta, that's opposite over hypotenuse, so that's y over r. Okay, so the formulas that we get here, we can get formulas exclusively for x and y just by multiplying these r's across. So we get x equals r cosine of theta, and y equals r sine of theta. Okay, and these are the two primary conversions that we use in polar coordinates. Okay, so it's x equals r cosine theta, y equals r sine theta. So these conversions, we've actually seen this all along when we use the unit circle, right? We know that the cosine value is the x value, and the sine value corresponds to the y value. So it's the same thing, just now generalizing to any radius. Okay. Using these relationships, we can actually find a couple of other formulas here. So if we want to find r squared, well, in the formulas up here, we have, if we factor out the r, actually don't even factor out the r, if we just square each of those, they're going to give us r squared times cosine squared plus sine squared, which is 1. And so this formula is actually becomes x squared plus y squared. Okay, so this is another relationship that we have, we're able to use. Okay, and this one should look just like the equation of a circle, right? Centered at the origin, and that's what it is. We can also, using the triangle, we can find the tangent value as well. So tangent of theta equals opposite over adjacent, so that's y over x. Okay. So here's a few formulas for us to be able to use. So let's look at some conversions here. So convert the point 2 comma pi over 3 from polar to Cartesian coordinates. So we want to go ahead and convert r's and thetas into x's and y's. So let's just use the formula we had for x and y. Oops. So x is r cosine theta. So that's going to be 2 cosine of pi over 3. Cosine of pi over 3 is 1/2, so 2 times 1/2 which is just 1. Okay. And y is r sine theta, which is 2 sine of pi over 3. And sine of pi over 3 is the other one. It's root 3 over 2. So that's 2 times root 3 over 2, which is just root 3. So the point in polar coordinates, 2 comma pi over 3, corresponds to the point in rectangular coordinates, 1 comma root 3. Okay, so that is our answer. Okay, let's look at this next one, now going the other direction. So we are given the point 1, negative 1 in terms of polar coordinates, or excuse me, in terms of Cartesian coordinates, and we want to try to express this in terms of polar coordinates. Okay, so let's go ahead and use a conversion. Now, x equals r cosine and y equals r sine, not as useful on this one, because we're given the x and the y, and we're trying to find the r and the theta. So what we can do is use those other formulas that we looked at. So we know that r squared equals x squared plus y squared. So that's going to be 1 squared plus negative 1 squared. So that's just 2, so r, take the square root of both sides, is the square root of 2. Okay, we don't need the negative square root of 2 here. Okay. And then we're looking at, because if we were going to use the negative, we would have to rotate the angle some more. So we just let the angle tell us where we are, rather than trying to make plus and minus for the r values. Okay? And then we can use the x and y coordinates to find theta using our tangent formula. So tangent of theta is y over x, so that's negative 1 over 1, which of course is just negative 1. Now, the trick with some of these problems, especially when solving for theta like this and using tangent, is that tangent has multiple angles that produce a value of negative 1 on the interval from 0 to 2 pi. So we have to make sure we choose the correct one in order to get the right answer. So we need to notice where this point is in the graph, and that'll tell us which angle to choose. Okay, so since, put this over here, so since the point 1, negative 1 is in had some trouble here. Since this is in the fourth quadrant, we choose the value where tangent is negative 1 in the fourth quadrant. So that would be theta is 7 pi over 4, or you can write it theta is negative pi over 4. Okay, so once we have that value, now we can go ahead and set up our point. And we can do this using either of the theta values. They'll be equivalent. So our answer would be either root 2 comma 7 pi over 4 or root 2 comma negative pi over 4. Okay. All right. So let's take a look at the next page here. So polar curves. So we can also not only plot points using polar coordinates, we can graph curves with polar coordinates. So let's take a look at what we can do here for ordered pairs r theta. So what curve is represented by the polar equation r equals 2? So in this case, notice that theta is not specified. So since we're not specifying what theta is, then we can just let theta be anything. Okay, so it can be anything. And then r, so that means we're going all the way around, right, 0 to 2 pi. And then r represents the distance from the pole, right, or the origin, if you will. Okay, so what does this give us? Well, we know that the angle is all the way around 0 to 2 pi, and the r value is the same no matter what. It's always radius of 2. So this gives us a circle. It gives us a circle of radius 2. So roughly there. So this is the equation. This is the curve r equals 2. Okay, and so like for example, if you wanted to have like r equals 1, you could just put, right, a circle of radius 1. R equals 1/2 would be a circle of radius 1/2 in here. So when you have an unspecified theta value and you just have r equals a constant, that's a circle. Okay. What curve is represented by the polar equation theta equals 1? So theta equals 1. So in this case, we know that the polar angle, so that angle of rotation is 1 radian, and we're always working in radians here. So, but the r value is unspecified, right? There is no r in there, so but r can be anything. Okay, so in this case, so let me draw my polar axis there. So we have 1 radian, looks something like this. And the r value can be anything. So it can go as high as we want it to, or it can be as negative as we want it to. And what have we created? We've created a line. So this is a line. Okay, and then you can see here, right, there's our origin O. We can go up, 1, 2, however many units we want. So this would be the point. This would be the point, right, 1, 1, right, 1 radius, right, r is 1, theta is 1. This one would have radius of 2, theta is 1. This one would have radius negative 1, theta is 1. This would have radius negative 2, theta is 1, etc. Okay, so this does give us a straight line. All right. So next up, let's look at a little more complicated example here. So sketch the curve with polar equation r equals 2 cosine of theta, and then find a Cartesian equation for this curve. So the first thing that we're going to do here is we are going to plot some points. Okay, so we're going to look at some theta values and some corresponding r values, which is 2 cosine theta. Right, that's given in the equation up here. So we're just going to pick a bunch of theta values and look at what happens when we choose them. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9 values here. So 1, 2, 3, 4, 5, 6, 7, 8, 9 down there. So just pick some common ones, some ones that we would know relatively easily. So 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. Okay. And I am just going up to pi because you'll see in just a second, but if we start going around to 2 pi, the shape is actually just going to repeat itself. So we don't need to do that. So let's go ahead and find some of these. So 2 cosine of 0. So 2 cosine of 0. Cosine of 0 is 1, right? So 2 times that is just 2. 2 cosine of pi over 6. Cosine of pi over 6 is root 3 over 2. So that's just going to be root 3. Okay. And then cosine of pi over 4 is root 2 over 2. So 2 times that, that's just root 2. Okay. For pi over 3, so you go through this whole pattern. Pi over 3, cosine of that is 1/2, times 2 is just 1. Cosine of pi over 2 is 0, times 2 is 0. Cosine of 2 pi over 3 is negative 1/2, times 2 is negative 1, etc., etc. So then we're going to get negative root 2, negative root 3, and negative 2. So a bit of symmetry going on here. Okay, so let's plot some of these. So go out 1, 2. All right, let me make this a bit bigger. All right, so let's plot some of these points. So for 0, actually let me get my angles in here first. So shrink that back down. Do these in blue. So I want, this is my pi over 6. You're going to make these dotted because they're just kind of a placeholder. But it's going to be easier for me to draw them out as a whole. Something kind of like that. And you're not going to need that bottom quadrant, and you'll see why in just a little bit. Okay. All right. So let's go back and let's plot these points now. So 0, 2, that's going to be out here. Pi over 6, root 3. So root 3 is a little bit bigger than 1, so that one's going to be right around there. Pi over 4 comma root 2, that's a little bit less than 1, so that's going to be like right there. Pi over 3 comma 1, so that's going to be right about there. Pi over 2 comma 0, so the angle pi over 2, of course, is this one up here. That's pi over 2 up here. So, but its radius value is 0, so that's going to be all the way back down here at the origin. And now, so 2 pi over 3, that's going to be this one over here. But because the radius value is -1, we're going to go along this same line down here into the negatives. So that's going to have, so a -1, that's going to be right about there. And then 3 pi over 4, again, that's this one. Or excuse me, that's this one. But we have a negative radius value, negative root 2, so it's going to be down here. So that's going to be right about there. Okay, and then 5 pi over 6, again, is this branch, but we're on the negative side of it because the radius is negative, so negative root 3. It's going to be right about there. Okay. And then we have pi comma -2. So pi is, of course, out here, but we're on the negative side, so that actually just brings us right back to where we started. Okay, so, oops. So this is going to be, right, theta equals 0 and theta equals pi are both out here. So let me go ahead and just write the points on here. That'll be a little more clear. So this is the point 2 comma 0. Remember, r always comes first. This is, get rid of these, whoops. This is the point root 3 comma pi over 6. This is the point root 2 comma pi over 4. This is the point 1 comma pi over 3. Right, 0 comma pi over 2. -1 comma 2 pi over 3. Negative root 2 comma 3 pi over 4. Negative root 3 comma 5 pi over 6. And then, of course, back to where we started, -2 comma pi. Okay. So now if we connect the dots here, and I'll try to draw this as smoothly as I can, you might be able to see what we're drawing here. It is a circle. Okay. So this does give us a circle that is not centered at the origin, right? It's actually a little bit off center. That has a radius of 1, it looks like. Okay. So for this case, if we want to find the Cartesian equation for this curve, we need to get a little creative with our formulas, with our substitutions that we can do. So we need to know what the x value and y value are, right, as a formula. So we don't want it in terms of r and theta anymore, so let's go ahead and start playing around with what we know. So we know that x equals r cosine of theta. So what that tells me, if I can replace the cosine theta, that would be really great. So I'm going to write cosine theta is x over r. Okay, so get that from that formula. So then coming from our original formula up here, right, r equals 2 cosine theta, so r equals 2 times x over r. So r equals 2x. Okay, or excuse me, r squared. Right, because multiply this r across over to there, that gives us r squared. And r squared we know, right, r squared, that's going to be x squared plus y squared. So that equals 2x. So now we kind of cut out this piece that we don't need anymore. We don't need the r. And we have x squared minus 2x plus y squared equals 0. You can go ahead and complete the square on these x terms. That's going to give us x minus 1 squared plus y squared equals 0. And this would be our equation in rectangular coordinates. So, what is this the equation of? Well, this is a circle with center 1, 0, and radius 1. So it is in fact what it looks like. It's a circle that's a little bit off center, right? It has a center of 1, 0, and it has a radius value of 1. Okay. Sorry. That should, when we complete the square, that should be a 1. Apologies. That should be a 1. That should be a 1. There we go. That gives us a radius of 1. I'm like, wait a second, radius of 0? That doesn't make any sense. That's right, it doesn't. So, yeah. So we plotted some points. We got a rough sketch of the curve, which in this case is a circle, and then we were able to convert it into a form that we understand a little better, those rectangular coordinates that we've worked with for all of our mathematical careers. Okay. All right. So let's go on. So sketch the curve, r equals 1 plus sine of theta. Okay, so one trick that we're going to start using now, rather than doing all that plotting of points, because plotting points is not very efficient, we're going to go ahead and just sketch the curve out in Cartesian coordinates first, and then use that to give us a really quick guide for what the curve is going to look like, and get some points for our r and our theta. Okay, so put this right here. So let's sketch in Cartesian coordinates so we can see the values faster. Okay, so nothing really different about this. We're still finding values of theta and r, but we're plotting it in a more rectangular sense so that we can see a little bit faster than just plotting points. Okay, so here's theta, here's r, and we're plotting the curve r equals 1 plus sine of theta. So I'm going to put just a few main values here. So that's going to be pi over 2, pi, 3 pi over 2, and 2 pi. Okay, and then notice this is going to be the sine curve, but shifted up 1 unit. So I'm going to go up 2 here. So that's 1, 2. All right, so the sine curve starts normally at 0, 0, but it's been shifted up 1, so it's going to start up here at 0, 1. Okay, and then it's going to oscillate, so it's going to go up 1 unit by the time it hits pi over 2, then back down to 0 at 3 pi over 2, and then back up to 1 when we hit 2 pi. So we get something kind of like that. Okay, so that's just our sine curve shifted up 1 unit. So when we're looking at how to sketch this in polar coordinates, okay, so do this over here. We need to look at what happens to these different values. So To start us off, so as theta goes from 0 to pi over 2, so over here, as theta goes from 0 to pi over 2, what happens to the r value? The r value goes from 1 to 2, so r goes from 1 to 2. Okay. So what does that tell us? Well, that tells us when theta is 0, r is 1. So that we knew that right off at the beginning here. So let me get my values in here. So 1, 2, 1, 2, 1, 2, 1 down there. Okay, so we start off at theta equals 0, and it has a value of 1. Okay, and then it goes up as theta goes to pi over 2, which is up here. R goes to 2, so 2 units up there. So that's going to look something like that. If I can kind of put a nice curve on it there. Okay. Good enough, I guess. So then, if we continue this pattern, so as theta goes from pi over 2 to pi, so theta equals pi is out here. Then we go from 2 to 1 on our outputs. So as we go around, this one brings us back to 1. So down to 1 over here. Something like that. Then as we go from pi to 3 pi over 2, theta goes from 1 down to 0. So here's theta equals 3 pi over 2 down here. Goes from 1 to 0. So 0 is right in here. It's right at the origin. So this is going to loop in like that. Kind of like that. And then from 3 pi over 2 to 2 pi, we go from 0 to 1. So we're going to go back out to where we started. Okay, and then so of course we start at theta equals 0, and we're going around the curve like this. So this particular shape, it has a special name. It's kind of a more common one that we encounter. This is called a cardioid. It's called cardioid because it looks kind of like a heart. So if it was drawn a little more smoothly, it would look kind of like that. Okay, so this is a cardioid, and that's kind of the method that we're going to be using to sketch out these polar curves. So let's look at one more. So let me separate that off there. So sketch the curve r equals cosine of 2 theta. So we need to first sketch out the graph of cosine of 2 theta on a rectangular set of coordinates. So that's going to be right here. So there's theta. There's r. And this is just the graph of cosine, but because it's got a 2 in the middle, so if anybody remembers your transformations, that means that it's actually going to get compressed. So it's going to be growing twice as quickly. So this is going to give us, so it's going to go, here's 1 to -1. So cosine, actually I'm going to plot a bunch of these on here. So we're going to count up by pi over 4s all the way up to 2 pi. So I need 8 of these. So 1, 2, 3, 4, 5, 6, 7, 8. So there's pi over 4, pi over 2, 3 oops, 3 pi over 4 pi, 5 pi over 4, 3 pi over 2, okay, 7 pi over 4, and then 2 pi over here. We'll graph these in purple. So cosine values start off at 0, 1 up here, and then it's going to go through the axis at pi over 4, or excuse me, at pi over 2. It's going to hit -1 at pi. Oh no, I apologize. I was right. I said it right the first time. Because this one's growing twice as fast, right? So normally it would go 0, pi over 2, pi, etc. But this time it's growing twice as fast, so it's going to hit the axis of pi over 4, then pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. So the curve's going to look something like this. So we get a couple of oscillations here in the curve. Okay, so this is going to allow us to get the values for our polar graph. So in this one, this graph is actually pretty interesting looking. So let me get this up here. So when we start off at 0, so there's 1, 1, 1, and 1. So when we start off at theta equals 0, so that's over here, we are going to be at 1, right? Because that's what we see up here, is theta is 0, r is 1, so that's going to be right here at 1. Then as theta goes to pi over 4, so let me just draw these, and you should probably make these dotted. Okay, so that they don't distract too much from the graph. Okay, so as we go to pi over 4, we're going to hit 0, so that's going to be right here. So this stretch of the graph is going to look like this. And then as we go to pi over 2, we go to -1 down here. So remember, when it's negative, the r value doesn't go up here like this. It actually goes opposite side. So we're going to go to -1, which is down here. Okay, so this is going to go like that. Then as we go to 3 pi over 4, we're back up to 0. So this is 3 pi over 4, brings us back to 0. Okay, and then at pi, we're back at 1, so that's out here. And then at 5 pi over 4, right, so that was pi. 5 pi over 4, we're at 0 again, so that brings us back to the middle. And then at 3 pi over 2, we're at -1, so theta equals 3 pi over 2 is down here. So, but it's -1, so we're actually going the opposite direction, so that's going to be up here. Kind of like that. At 7 pi over 4, we're back at 0 again, so 7 pi over 4. Oops. 7 pi over 4 down here. So that brings us back to 0 again. And then when we go to 2 pi, of course, we're back at 1, which brings us right back to where we started. Okay, so this is the first, second, third. It's one continuous. If you graph this as a parametric equation, you'll see that it traces out this very nice smooth curve. This one also has a special name. This is called a four-leaved rose. So just another special graph that we like to look at here. So that's tracing it out using that polar equation, okay, that polar curve there. All right. So symmetry, the next topic here, we're just going to briefly touch on symmetry. We're not going to do a whole lot with it. This is just to help make the graphs a little bit easier to draw sometimes. So if a polar equation is unchanged when theta is replaced by negative theta, we say the curve is symmetric about the polar axis. Okay, so if we notice that theta and negative theta both produce the same value, the same equation, then it is symmetric about the polar axis. So again, that's like the positive x-axis. And then if the equation is unchanged when r is replaced by negative r, or when theta is replaced by theta plus pi, those have the same effect, right? Because if I take, here's r, or negative r, points the other direction, or I take, this is theta right here, and then theta plus pi is down here. Okay. Then the curve is symmetric about the pole, right, or that origin point. And part C, if the equation is unchanged when theta is replaced by pi minus theta, the curve is symmetric about the vertical line theta equals pi over 2, right? And so if that's x, then this is our line, right? Theta equals pi over 2. So we would have some symmetry about that. You can look at the symmetry of the ones we've done above, right? The cardioid was symmetric about that line, pi over 2, right? If you just drew the vertical line right there, that is symmetric. Okay, so we can look at the symmetry of a lot of different ones, but we're not going to take a lot of time to focus on those. Okay, and then the last topic for this section, tangents to polar curves. So of course, we can't talk about polar coordinates without doing a little bit of calculus on polar coordinates. So to find a tangent to a polar curve r equals f of theta, use theta as a parameter and write it in its parametric form. So we have x equals r cosine of theta, but r is a function of theta, so this is f of theta cosine of theta, and y is r sine theta, which is just f of theta sine of theta. Okay, so this allows us to work with x and y exclusively in terms of theta. So if we want to take the derivative, well, this formula that we're going to have here for the derivative is just like the one we had for regular parametric equations. So if you go back and look, you'll see it's the same thing as with t, except now it's theta instead of t. So dy dx, that's just going to be dy d theta, so derivative of y with respect to theta, over dx d theta, so derivative of x with respect to theta. So to find where the tangent lines are horizontal, we're looking for this whole thing to be 0, which means the numerator has to be 0. So where dy d theta equals 0. And to find where tangents are vertical, it has to be undefined, so the denominator would have to be 0. So dx d theta equals 0. And that's assuming the numerator is not 0 at that same time. Okay. So armed with this, let's go ahead and head into our last example here. So hopefully we have enough space. It's kind of a long-winded one here, so let's get right to it. So to start us off, so part A here. So x is r cosine theta. So we have the cardioid r equals 1 plus sine of theta. Find the slope of the tangent line when theta equals pi over 3. So x is r cosine theta. So that's going to be 1 plus sine theta times cosine theta. Okay. Or, right, this expanded out, we get cosine theta plus sine theta cosine theta. We have, we have y is r sine theta. So that's 1 plus sine theta times sine theta. So that's sine theta plus sine squared theta. Okay. So now we want to take the derivative of these. So we get, so I'll just do, so dx d theta, that's going to be negative sine of theta plus sine times cosine, so we have to do the product rule on this one. So first times derivative of the second, so that's actually going to be minus, so minus sine squared theta plus derivative of the first times the second, so that's plus cosine squared theta. Now, we want to try to simplify this as much as possible, and this, I would love to be able to use the trig identity sine squared plus cosine squared. However, this sine squared is negative, so we can't do that so much. But what I can do is I'm going to go ahead and convert the cosine squared into 1 minus sine squared theta, and that's going to put everything in terms of theta. Okay, or excuse me, in sine of theta. So this is going to be, I'm going to move the 1, when I sub it in, I'm going to move it all the way to the front. So that's going to be 1 minus sine theta minus 2 sine squared of theta. Okay, and that is actually factorable. This is factorable as 1 plus sine theta times 1 minus 2 sine theta. So that's dx d theta. And then dy d theta, that's going to be cosine of theta plus, using the chain rule, that's 2 sine theta cosine theta. Factor out a cosine, we're left with cosine theta times 1 plus 2 sine of theta. Okay, so this is dy d theta. So our general formula for the derivative, so dy dx, is dy d theta over dx d theta. So that is cosine of theta times 1 plus 2 sine of theta over 1 plus sine of theta times 1 minus 2 sine of theta. Okay. And now we are trying to evaluate this, right? Because remember the question's asking for the slope of the tangent when theta equals pi over 3. So we're going to go ahead and just do it right here. Evaluate at pi when theta equals, when theta, write this down properly, when theta equals pi over 3. Okay, so let's just go ahead and evaluate at pi over 3. So that's cosine pi over 3 times 1 plus 2 sine pi over 3 over 1 plus sine pi over 3 times 1 minus 2 sine pi over 3. So now we need to remember what sine and cosine of pi over 3 are. So cosine of pi over 3 would be 1/2, and sine of pi over 3 is root 3 over 2. So this is going to give us, so 1/2 times 1 plus 2 times root 3 over 2, so the 2's cancel, so just 1 plus root 3 over 1 plus root 3 over 2. Oops. Sorry. Root 3 over 2. I made it to the to the very bottom of the page here. 3 over 2. That's not going to work. Times 1 minus root 3. There we go. Good enough. Okay. If we play around with the algebra a little bit and just go ahead and simplify this, so I would pull the 1/2 out here and multiply the 2 into this one. So let me just show you. Leave this intact right here. Sorry, we're kind of condensed on space on this one. But this would give us 1 plus root 3. Pull the 1/2 out and bring it into this one, right? Because the 2 is in the denominator, so the 2 can go in here. That becomes 2 plus root 3 times 1 minus root 3. Multiply those out. That gives us 1 plus root 3 over negative 1 minus root 3. Which, of course, is 1 plus root 3 over negative 1 plus root 3. If you factor out the negative 1, those cancel, and we're left with negative 1. So it turns out, in answer to the question, for that cardioid, the slope of the tangent line when theta equals pi over 3 is negative 1. And if we go back and look, right, at pi over 3, that was right about, if I can get this right about here. About there. So we can see the slope right there is about negative 1. Right, so let's go back. So if you need to take a look, because obviously I'm out of space, we need to do part B. So if you need to take a screenshot of this or pause it, write all this down, do so, because I'm about to erase it, so you can go back and look in the video if you want to see this stuff again. But basically, just a reminder what we did. We found the x, we found the y, got their derivatives, plugged those into the formula here for dy dx, and then solved and got the slope to be negative 1. Okay? All right, let me get rid of all of this. Okay. And then just clean up some of the leftovers here. Okay, so now we're going to look at part B. So, and that says, find the points on the cardioid where the tangent line is horizontal or vertical. Okay, so in order for it to be horizontal, we need so this is part B, we need the dy d theta to be 0. So that was cosine theta times 1 plus 2 sine theta. That is going to be 0 when theta has the following values. So we can find when this is 0, that gives us theta is pi over 2, 3 pi over 2, 7 pi over 6, and 11 pi over 6. Okay, and then the vertical tangents, that's when dx d theta is 0, so that's going to be 1 plus sine of theta times 1 minus 2 sine of theta, and that equals 0 when theta is 3 pi over 2, pi over 6, and 5 pi over 6. All right. So notice We do have one overlapping value here, that's the 3 pi over 2. This claims that there's a vertical and horizontal tangent there, so we're going to put that on pause for just a second. We will come back to that momentarily. But for now, let's just establish what our tangents are. So our horizontal tangents at the points. So corresponding radius values, we can go back and get those from the cardioid, but that's at pi over 2. So 2 comma pi over 2 at 1/2 comma 7 pi over 6 at 1/2 comma 11 pi over 6. Okay, and then our vertical tangents are at, again, we'll put the 3 pi over 2 on hold for a second, but that's going to be at 3/2 comma pi over 6 and at 3/2 comma 5 pi over 6. Okay. There's that symmetry showing up there. So those would be our vertical tangents. Now, for the 3 pi over 2, if both of them are 0, this tells us that dy dx is 0 over 0. This particular type of fraction, this is what we call indeterminate. You might recognize this form from Calc 1 when we used a particular rule to help solve these, and that was L'Hopital's rule. We actually are going to use L'Hopital's rule here to help determine what's actually happening at this point as we approach 3 pi over 2. So we're going to approach it from the left and use the symmetry to say what happens on the right. So we're going to take the limit as theta approaches 3 pi over 2 from the left of dy dx. Okay, so what that gives us is going to be the two pieces here. So let me rewrite this. So we're going to split this into two limits here, okay, because our dy dx, notice the numerator, the dy d theta, has this piece times this piece. Denominator has this one times this one. So what I'm going to do is I'm going to group these two together, and I'm going to group these two together, okay, and split up the limit across that product. Okay, so we have the limit as theta approaches 3 pi over 2 from the left of 1 plus 2 sine theta over 1 minus 2 sine theta, and then limit as theta approaches 3 pi over 2 from the left of the other, so of cosine of theta over 1 plus sine of theta. Okay. So this one is not indeterminate. That's not the part that gives us the problem. So if you plug in 3 pi over 2, you get sine of 3 pi over 2 is -1. So that gives you 1 minus 2. So 1 minus 2 over 1 plus 2. So that becomes -1 over 3. So this becomes -1/3 times the limit as theta approaches 3 pi over 2, and that's why we split it up. In case you were wondering, like why would we do that? Because not the whole thing was indeterminate. It was just part of it. Okay, so now we can work with this one and perform L'Hospital's rule on it. So perform L'Hospital, so we take the derivative of the numerator and the denominator separately. Limit as theta approaches 3 pi over 2 of negative sine of theta over cosine of theta. Okay, and we're approaching from the left. So now, as theta approaches 3 pi over 2 from the left, we can see that the sine values are getting closer and closer to -1, so the numerator is heading towards 1, and the denominator, the cosine of theta, is getting closer and closer to 0. And if the denominator is getting really, really small, that means the numerator, the whole term is getting really, really big. So this is actually going to be growing infinitely large as we head towards 3 pi over 2 from the left. So this actually equals infinity. Okay, so it's growing infinitely large as we head towards 3 pi over 2 from the left. Now we do have symmetry here, so by symmetry, okay, the limit as theta approaches 3 pi over 2, so 3 pi over 2 well, at least you know what I'm trying to write. 3 pi over 2 from the right of dy dx. That symmetry actually will tell us that this is going to be negative infinity. So as we approach from the left, we're heading towards positive infinity. As we approach from the right, we're heading towards negative infinity. Remember, these are the slopes, right? So as we come from the left on the cardioid, we're heading towards positive infinity. As we leave it from the right, we're heading towards negative infinity. So this gives us a vertical tangent, right? It's purely vertical, heading towards positive and negative infinity. So this gives us a vertical tangent. So we can go ahead and add it to our list of vertical tangents. So it turns out it's not a horizontal tangent. It is just a vertical tangent. So that gives us the point 0, 3 pi over 2 is also where a vertical